Hello everyone. In this video, I am going to explain you discrete cosine transform, which is a topic of digital image processing. Now, discrete cosine transform, DCT is similar to discrete Fourier transform. That means DCT and DFT are similar. DCT transform a signal or image from spatial domain to frequency domain. So what DCT does? Discrete cosine transform an image from spatial domain to frequency domain. Same is possible by DFT. What DFT does? DFT also transform a signal or image from spatial domain to frequency domain. Then what is the difference between two? The difference between two is type of basis function. In both the transform, basis function is different. The basis function used by each transform. DFT uses set of harmonically related complex exponential function, while DCT use real valued cosine function. What is the meaning of this? Let's start with this first statement. The difference between two is type of basis function. What is meaning of basis function? Now, let's take the formula of two-dimensional DFT. In this formula, you can see this part. This is nothing but this part is known as basis function of that transform. It is in the form of e raised to power minus j theta. It is in the form of e raised to power minus j theta. So what is written? Difference between two is type of basis function. This basis function is different. DFT. This is formula of DFT. DFT uses harmonically related complex exponential function. So e raised to power minus j theta, it is complex exponential function. There is real part as well as imaginary part available. It is sine theta minus j sine theta. What it is? Sine theta minus j sine theta. So it is real as well as imaginary parts are available. Wherein DCT uses only real valued cosine function. Now let's see the formula of DCT. This is formula of DCT, sorry. You can see this is basis function of DCT. In this basis function, there is no exponential term available, only cos term is available. And this cos term is a real function, it is real value, there is no imaginary value included in this. And hence it is said that DFT is complex and DCT is a real valued function. So this is the difference between DCT and DFT. Otherwise, both transform image from spatial domain to frequency domain. What is discrete cosine transform in image processing? What is DCT? The discrete cosine transform represents an image as a sum of sinusoids of varying magnitudes and frequencies. What discrete cosine transform does? It represents image as sum of, that means an image as a sum of sinusoids of varying magnitude and frequency. Let's take an example in this. You can see here this one sinusoidal signal is shown as addition of two different varying magnitude and frequencies. You can see the one signal, this particular yellow colored signal is shown. It is nothing but the addition of two sinusoids of varying magnitude and frequency. And same is the job of discrete cosine transform. Now what DCT does? Discrete cosine transform helps separate the image. What it does? It separates the image. Which image? Let's take an example of this image. Into parts of differing importance. That means we can separate this image into parts of differing importance. Differing importance, but by means how? With respect to image visual quality. With respect to image visual quality. That means by using DCT, we can separate this image into different parts. You can separate this image into different parts like this of differing importance with respect to image visual quality. What is meaning of differing importance? Now, if you have a look on this image, Now, don't you think this particular part of this image is not important? There is nothing. You can see here, this particular only wall is there. This particular part of image is of no importance. There are no variations. Only one pixel intensity level is available. If you see this part, this is also not very important. But if you see this particular part, which is a Lina image, it is a human figure. Lot of variations are available. The cap is there, the circular part is there, hair part is there, eyes, nose. So lot of variations and pixel intensity variations are available in this particular area, and hence you can say that the human figure in this particular image, the human figure is more important than this background. Whatever background is there, because you see this particular area, there are no pixel intensity variations available. Similarly, in a human figure also, if you see this particular area, there is no pixel intensity variation available. Even you see the cheek, this part, there is no pixel intensity variations. But if you see this particular part, or eyes, or nose, or this hair part, so pixel intensity variations are available. So every part is of different importance according to visual quality, and DCT helps to separate the image into parts of differing importance like this. So we are going to learn in detail about this image in the coming slides. DCT is often used in image compression application. So what is the application of DCT? It is used for image compression. For example, DCT is used in international standard lossy image compression algorithm known as JPEG. So whatever JPEG image we use, in that JPEG images, this DCT based image compression technique is used. Now, two-dimensional DCT is given us. What is the formula of two-dimensional DCT? Let's consider n by n image. That means it is there are n number of columns and n number of rows in the image. So what is formula of DCT? It is given as, actually it is f of u comma v. It is, sorry, this is f of u comma v equal to au into av summation, double summation, wherein x and y both varies from 0 to n minus 1, f of x comma y. What is f of x comma y? This f of x comma y is nothing but image. This is your image, this n by n image. There are x comma y. Cos of 2x plus 1 u pi divided by twice n, cos of again 2y plus 1 v pi by twice, wherein u and v both varies from 0 to n minus 1. That means if image size is 4 by 4, then u and v and x and y will vary from 0 to 3. If image size is 8 by 8, then u, v, x and y all will vary from 0 to 7. Now what is this? AU, this is given by, AU is root of 1 by n if value of u is equals to 0. And it is root of 2 by n for u equal to 1 to n minus 1. That means for u not equal to 0, you have to use this value. Now what is AV? What is this AV? AV is again say 1 by n. For, this is not for v equal to 0. This is, yes, it is v equal to 0 and root 2 by n for v from 1 to n minus 1. The n by n cosine transform matrix is defined as, so how this n by n cosine transform matrix is defined like this CUV. It is defined as again under root of 1 by n for u equal to 0. So here it is, this it was correct. Okay, this is v equal to 0 only. And here it is C of u comma v equal to under root 2 by n, and this cos pi 2v plus 1 into u by twice n, wherein u varies from 1 to n minus 1, but v varies from 0 to n minus 1. If you solve this, if you put in the values and calculate, then you will get this matrix for 4 by 4 image. If your image size is 4 by 4, that means if n is equals to 4, then you will get these values if you calculate all this. Now what you have to do, the two-dimensional DCT, discrete cosine transform of image, can be generated by using equation. So equation is f equal to c. That means you have to use this matrix, then take f. F is nothing but this your original image, f of x comma y, into transpose of this matrix again, matrix transpose of same matrix. So this formula you have to use while calculating discrete cosine transform of an image. Now, what is two-dimensional DCT basis signal? As I said, the DCT is used to separate the image into different parts of varying importance. So how? So two-dimensional DCT basis signal, let's consider n is equals to 8. That means we are considering n by n image. For n by n image, the C UV is given by, this is horizontal frequency V and this is vertical frequency here U. Now here these values are V is equals to 0, V is equals to 1, V is equals to 2 and so on for up to 7, because U and V varies from 0 to n minus 1. Our n is 8, so it will vary from 0 to 7. U is also varying from 0 to 7. Okay. Now each image in the figure is 8 by 8 image. So each image means this, every image is 8 by 8 image. So this particular image is for U equal to 0. This particular is for U equal to 0 and V equal to 0. That means if U and V both are 0, you will get this image. Okay. Now V equal to 1, U equal to 0, you will get this image and so on. Each image in the figure is 8 by 8 image, hence there are 64 possible images. So there are 64 possible images. Because U and V both are varying from 0 to 7, so total there are 64 possible images. And each represents 64 basis functions of 8 by 8 image. So these are possible images. This represents 64 basis function. All these images are nothing but basis function. Basis function that we have this basis function that we got from this formula. So these are basis functions. That means we can decompose image into 64 basis function. We can decompose a single image into 64 basis function. And these basis functions are fixed. We cannot change this basis function according to these positions of U and V. That means for U equal to 0, V equal to 0, this image will be like this always. So these basis functions are fixed. Now, if the consider our image is completely black. Image is completely black. So it is 8 by 8 image with 8 pixels in the column and 8 pixels in the row, say, and this image is completely black. There is no variation. So, and if we calculate the discrete cosine transform, we will get C00. That means U equal to 0 and V equal to 0 because there are no variations in the pixel intensity values. If image has lots of variations, as I have shown you earlier image, like that is Lina image. The Lina image has lots of variations everywhere in the image. So in that case, you will, if you calculate DCT, you will get its basis function will be like this, and so on. So how to understand it? The distribution of coefficient in DCT. How these coefficients, these are coefficients, how these coefficients, these are coefficients, and how these coefficients of DCT are distributed. So you can see, as I said, if there are no variations in the image, you will get DC coefficient. DC coefficient means there are no variations. Okay, no frequency variations. If there are minor variations in the gray intensity values in the image, you will get this spectrum like this here. Now this indicates, the green portion indicates mid frequency. That means little more variations in the gray intensity level. In the image, if there are little more gray intensity variations, you will get the DCT in this particular area. In this particular area means here. In this image, if you see, it will be here. And as I said, if there are huge number of variations in the image, then it will be in this particular area. Means high frequency variations. That means if there are lot of variations in gray levels like white, black, again white, again black, again white, again black, in horizontally changing, vertically changing, in all directions the gray intensity are changing, then you will get this kind of DCT. Your coefficients will be in this particular area. Consider this example. This is a simple scene, and if we take a small block from this image, suppose this is 8 by 8 block where there is only sky, only one color, blue, there are no variations. And if you take a DCT of this, you will get like this, a low frequency in this particular area, because in sky there will be a little variation in the blue color. So your DCT will be in this area. So similarly, now you can relate. If there are no variations in the image, the DCT coefficients will be like this. And if there are huge number of variations, it will be in this particular area. Here also you can see lot of variations. Otherwise, in the middle portion. Now let's take an example for more clarity. If this is image, this is 8 by 8 image, you can see the variations are in this direction, and only once the image is changing the color. Here it is black and here it is green. So variations are in this direction. So your DCT coefficients will be like this. Similarly, if you see this image, suppose this is image, now here variations are in this direction. Now variation is not in this direction because here it is completely black, here it is completely white. Now in this direction it is changing from black to white. So your DCT coefficients will be like this. Here variations are more, so you can see DCT coefficients are also like this. The basis function is like this. Again, in these variations are in this direction, so you can see the DCT coefficient. Again, in this it is blur, very little variation, so you can see the changes. Here also it is very blur. So, but still variations are in this direction, and so on. So what exactly DCT is giving us the information? It gives us an information about in which direction the variations in black and white is more in the image. The way it is in DFT as well. Discrete Fourier transform also gives us the same information. It gives us an idea about in which direction the variations of black and white is more. Here also DCT is also giving us the same information. The frequency of variation, that what we call it as frequency. Now let's consider discrete Fourier transform of this particular image. In this particular image, first we have to divide it into 8 by 8 blocks. And then after dividing into 8 by 8 blocks, find out DCT of every block. Find out DCT of every block. Now if you take this forehead part, there are no variations. Since there are no variations in the, or there are very little variations in the intensity values, now you know in which area, which kind of this DCT you will get. Now consider this particular block, which is an eyebrow section. So this is an eyebrow section, and if you find out the DCT spectrum, this is a DCT spectrum of this particular image. So these are pixel intensity. What is this? These are pixel intensity values of this particular area where there is a half forehead and little part of eyebrows. Now you can see that the eyebrow part is in this area and here it is white. Okay. Now if you take if you calculate the discrete cosine transform, you will get something like this. What it indicates, if you see carefully, here the computed coefficient value in this area, it is high, it is 174. It is 174. And if you see in this area, it is like very less, 0, 1, -1 or negative. That means it is almost 0. In this area again it is little high, it is 1952, but it is lower than 174. So you can compare this image with this for better understanding. It is always like this. On the left top corner you will get a computed coefficient value, highest value of computed coefficient in DCT. Now let's take another sample. This is a part, a square of eye pupil some area, and let's see if you calculate the discrete cosine transform. So you will get something like this. So here also you can observe, here the values are higher on the left top, and here these are always lower side. So these are always lower side, black, and this is white. 70, 24, 70, 174 close to white, 70 close to you can say white only. And let's take this nose part. There are no variation in the pixel intensity value. These are the pixel intensity values, and if you calculate the node spectrum, DCT spectrum, again it is 174 and so on, and everywhere it is black. Why everywhere it is black? Because there are no variations in this. Now discrete cosine transform, let's take example. Now as you see this image, in this variations are more in this direction. So if you carefully observe it, you can see here like this discrete cosine transform. Now if you see this image, the variations are in all directions, in this direction, in this direction. The spectrum is also like this. In this image, there are variations again in all the directions. So you can see the DCT like this. Now let's solve an example of discrete cosine transform. Find DCT of given 4x4 image. So 4x4 image, f of x comma y is given. These are pixel intensity values, and we have to calculate DCT. Now remember the formula. What is the formula? Two-dimensional DCT of image can be generated by using equation f equal to c f c transpose. What is c? C is the cosine matrix. Now since image size is 4x4, we have to use 4x4 cosine matrix. I have already shown you how to calculate this cosine matrix, and that matrix is fixed. So what you have to do, you have to take this matrix, that is cosine matrix, same as I have shown you in the previous slides. Then multiply it with this image. This is image. And then this is transpose of this matrix. That means rows becomes columns and columns becomes rows. So what you have to do, you need to know how to multiply matrix with the matrix. First multiply this and this. You will get some solution. You will get one matrix, and then multiply that matrix with this matrix. Follow this procedure, and then you will get this final answer. So this is the final answer of discrete cosine transform of this particular problem. So this is DCT. Now if you see this DCT here also, you will see here at the corner there is higher value, and at other places it is negative values. So it is 0. So how the image will look like? The image will be like this. Images will be like this. Here at the white spot, and everywhere there will be black. Now why discrete cosine transform is used in image compression? Let's take a small example. Discrete cosine transform is used in lossy image compression. What is meaning of lossy image compression? The DCT works by separating images into parts by differing frequencies. Yes, we already understood that DCT works. It is used to separate the image into parts of differing frequencies. The image is broken into 8 by 8 blocks of pixel. Consider this image, it is divided into parts of 8 by 8 blocks. Now consider this small part. This is 8 by 8 block of this particular image. These are the pixel intensity values of this particular block. Then you have to take DCT. Calculate DCT of this. After calculating DCT, as I told you, here everywhere you will get either negative or black pixels. That means 0 value. and on this corner you will get higher values like this, somewhat like this. So you have got this. Then after that you have to quantize this image. After quantization you will get this. And after this you have to encode. How to encode? Write this value, then this value, then this value, then this value, then like this. So go like this. So see here. Now write these values in the sequence. So what is this? This is encoding of this particular 8 by 8 block. So discrete cosine transform is used for lossy image compression. Why it is written lossy image compression? Now you know that during quantization, the less important frequencies are discarded. So what we did in this, we have not written this 0, 0, 0, 0. We have written values, only these values. And we have discarded all these 0, 0 values while encoding. So during quantization, the less important frequencies are discarded. Here also, less important frequencies are discarded. And hence we use the word lossy image compression. DCT is the lossy image compression technique. That is, its large amount of information is stored in very low frequency component. You can see here large amount. This image can be represented as this sequence. This image 8 by 8 block is represented by this sequence. That is, large amount of information is stored in very low frequency component of signal, and rest other frequencies having very small data, which can be stored by using very less number of bits. So this can be stored by using very less number of bits as compared to this, and hence DCT is used for image compression. So I hope you understood what is DCT, why it is used for, what is the difference between DCT and DFT, how to solve problem on DCT, and what is the application of DCT. Thank you very much. Thanks for watching.